Hello, everyone. I'm Geng Hao from the Shanghai Tech University. Today, I will give a presentation about the work, the Pareto-driven tool parameter auto-tuning in physical design by Gaussian process transfer learning. This work is done by collaborating with Professor Qixu from USTC, Professor Songyi Hou, and Professor Bei Yu from the CUHK. Here are some backgrounds about the tool parameter tuning. Recently, the synthesis-centric VLSI design flow is facing increasing design complexity and suffering the pressure of time to market. EDA tools have been developed to aid and speed the closure of the IC design. They offer continuous tunable parameters that can significantly influence design quality. How to automatically find the optimal parameter configurations is a challenge. So it is important to develop the parameter auto-tuning tools. For a better understanding, we draw some visualizations for tool parameter auto-tuning. We can see that given design and the tuned parameter values and the other files like the constraint descriptions, technology file, the physical sensor tool can output the high-quality design. And during tuning, the tuning engine module will obtain some latent information from the physical design tool, like log files and the reports containing the QMNAR metric values to guide the whole tuning process. The left bottom figure just shows a grid sampling method is performed to select possible parameter configurations. Of course, for simplicity, only two parameters are sketched here. The right bottom figure just illustrates the QR metric space. I mean the area versus delay. And however, some issues may happen. For example, the final performance after physical synthesis could vary significantly under the delicate change of sensitive parameters. We can see there are two clusters in the QR metric space. Most of the dots in QR metric space show either an unsatisfied area quality with low delay or a small error value with high delay. I further list some general issues which may happen in tool parameter auto-tuning. For example, a lot of values of design parameters need to be tuned, and the multiple quality of result metrics like area, power, delay to be optimized. And besides, we may meet black box optimization problem, and even worse, the tool evaluation is time-consuming. Here I just list two pioneered works. The DAC 19 exploits a neural network and a tensor decomposition method, but it requires many data points for training. And the SPDAC 20 exploits with some trick to handle the multiple QR metrics. However, this kind of trick does not always work well. To search good parameter configurations and reduce the cost on tool evaluation, we may consider developing more efficient searching framework and exploiting the historic data set. Since the similar parameter configurations tried quite a few times in navigation of prior tasks, but some spatial issues may happen directly. First is how to design the searching framework to handle multiple objectives and save the runtime cost on the tool evaluation. And the second is how to transfer the current framework from the small designs to big designs. And our solution is that applying the Pareto-driven iteratively auto-tuning framework where the Gaussian process with transfer learning paradigm embedded. The solution can handle multi-objective optimization problem and not require too many samples for tool evaluations when it keeps the good quality of QR metrics of predicted the parameter configurations. Of course, it saves the runtime overhead. And here is a visualization of our proposed solution. The historical knowledge consists of the prior parameter settings and the associated PPA values. The transfer Gaussian process in the proposed PPATuner leverages knowledge, and the tuner will give the tuned parameter settings. So let's jump into the algorithm part. The first is machine learning model embedded in the PPATuner, the transfer Gaussian process. The main idea behind is to learn a transfer kernel to model the correlation of the outputs when the inputs come from the different tasks. So in other words, the building a measurement of similarity between different tasks. First, we can assume we have n tool parameter configurations for the source task and m instance for the target, and the f means the underlying latent function between the input and output, and we consider the joint distribution of the outputs of both tasks and define a Gaussian process on it. So now we get the kernel task for transfer learning. The intuition behind the kernel definition is that this additional factor makes a correlation between points of different tasks and are less or equal to the correlation between the ones in the same task. If 2 points, 2 configuration points xn and xm come from the same task, the factor becomes 0, and consequently, if them from the different task, it becomes 1. The parameter rho, which represents the dissimilarity between the source task and the target task will work. We may consider the rho is from a gamma distribution, and by integrating out the rho, the kernel matrix with some hyperparameters can be obtained. Therefore, by the Bayesian theorem, we can obtain the conditional distribution, and the mean and the covariance matrix of the last of the Gaussian process output just showed here. And to avoid boring, I ignored all the tedious calculations. You can refer to my paper for a more detailed description. And now we have described the transfer Gaussian process, and here is the whole flow of the proposed PPATuner. The PPATuner is to find the Pareto set by navigating the whole tool parameter configuration space. The historical data in the source task is exploited with a few parameter configurations in the target task to initialize the transfer Gaussian process model. And the whole auto-tuning algorithm works by iteratively performing the transfer Gaussian process model calibration, decision making, and the selection. The iterative refinement will stop when reach the maximum iterations or all the parameter configurations have been decided. Eventually, the predicted Pareto optimal parameter combinations will be fed into the physical design tools and then go through the physical design flow for evaluation. And we implement our algorithm based on the Python and the certain physical design tool employed in the paper is Cadence Unified implementation system. We designed two scenarios for transfer learning. One is given the same design according to the reason, like different designers' preference of final design quality. Distinct parameters will be considered to tune. And the other scenario is we call it the similar design. With similar but different size designs at hand, the faster transferring knowledge from smaller design to larger design is essential. So, we use three benchmarks in two scenarios. Here is statistics of the parameters of the physical design tool of utilized benchmark. And we exploit industry benchmarks under 7 nanometer technology node, where three of them, I mean the source 1, target 1, and source 2 are generated by the same multiply accumulate design with different parameters. And the target 2 benchmark is generated by the a much larger design. So here are some experimental results of two scenarios. We can see that the proposed tuner performs better than the other cutting edge algorithms in the two scenarios. And for a better demonstration, we draw the visualization of the Pareto frontiers in power versus delay space on target benchmark. And it shows that our method can find the Pareto points are much closer to the real ones than the other SOTA algorithms. And then in this work, we have proposed that the PPATuner, a Pareto-driven parameter auto-tuning flow of the physical design tool, which can adaptively transfer the knowledge from prior tuning tasks to new jobs via Gaussian process, machine learning model. And then in the future, we may consider more tools in other design stages and tune the parameters of tools simultaneously. That's all my presentations. And thank you for your listening.